Good morning. Myself, Guruswami K, Head of the Department of Physics, IDST Government College, Chikmagalur. In this video, I am going to deliver a third lecture on free electron theory of metals. This free electron theory of metal chapter belongs to the program 3rd BSc Physics 6th semester paper 7. The title of the paper is Solid State Physics and Electronics. Okay, before going to start to discuss the topics in this session, we should discuss the recap of the previous session. In the previous session, we discussed about the derivation of this Fermi energy at absolute zero temperature and derivation for average energy of free electrons at absolute zero temperature. Before that, we also discussed the explanation of N of E versus E graph for free electrons. Those topics were discussed in the previous discussion. In addition to that, we are also given expression for Fermi energy at absolute zero. Okay, now we are going to discuss in this session the topics like Fermi temperature, Fermi momentum, concept of Fermi velocity, application of quantum free electron theory to electrical conductivity, and collision time tau as a function of Fermi energy. These concepts were discussed in this chapter. Again, here a qualitative discussion connected with the Fermi temperature, Fermi momentum, Fermi velocity, okay, and application of quantum free electron theory of electrical conductivity and collision time tau as a function of EF. We may expect 2 marks question on all these topics, and we may expect some problems also connected with these. Okay. Now we are going to discuss one by one. First, we have to discuss concept of Fermi temperature. The temperature corresponding to Fermi energy is called Fermi temperature. The temperature which corresponds to the Fermi energy is called Fermi temperature, which is given by Tf is equal to Ef by K. Our Fermi temperature is defined as, okay, thereby the Fermi temperature is defined as, it is a ratio of Fermi energy to the Boltzmann constant. It is a ratio of Fermi energy to the Boltzmann constant is what we call the Fermi temperature, Tf. With the Fermi energy of the order of few electron volt, the Fermi temperature works out to be of the order of several thousands of Kelvin, which is approximately equal to 10,000s of Kelvin, that is 10,000 Kelvin or 10,000s of Kelvin. Okay, thereby, with small electronic energy, say the Fermi energy, we have to observe that the temperature of the metal should be of the order of 10,000s Kelvin. Okay, with very high temperature is given to the metal, thereby the energy gained by the electrons, the free electrons, is in the order of electron volt only. Here the Fermi temperature is not the temperature of single atom or electron. Here the Fermi temperature nothing but is not the temperature of a single free electron or an atom in the metal under consideration. It is the average temperature of free electrons at the Fermi surface. Okay, Fermi temperature is the average temperature of whatever the free electrons would occupying in the energy levels which are close to the Fermi energy or Fermi level. That temperature is what we call Fermi temperature. Next, we are going to discuss the concept of Fermi velocity. Fermi velocity. The velocity of the electrons which occupy the Fermi level is called Fermi velocity. Whatever the velocity acquired by the electrons which are present very close to the Fermi level or which are present in the Fermi level, say that velocity is what we call Fermi velocity, or the velocity associated with the free electrons at Fermi level is called as Fermi velocity. The expression for Fermi velocity is obtained by using the kinetic energy expression, that is at Fermi energy, that is E suffix f. Ef is equal to half mvf squared. This is general expression we use to calculate the kinetic energy. So the same expression is used to calculate the Fermi velocity and as Fermi energy. Thereby Ef equal to half mvf squared. Then Vf is equal to 2 EF divided by mO to the power of half. This is the expression used to calculate Fermi velocity. Expect some problems on this formula. Next, Fermi wave vector. Concept of Fermi wave vector. The wave vector k suffix f, Fermi wave vector, okay, corresponds to Fermi energy is given by h cross kf square divided by 2m. Again, this wave vector used to define the Fermi electrons, free electrons, which are present very close to the Fermi energy level. So, h cross kf square divided by 2m. These are all constant. H cross nothing but h by 2 pi, where h is the Planck's constant and k is the Boltzmann constant and m is the mass of the electron. Okay, that gives some constant vector. So, that vector is what we call Fermi vector. Next, Fermi momentum. By using the above expression, that is Fermi velocity or Fermi energy expression, okay, we are going to deduce an expression for Fermi momentum as Pf is equal to 2m Ef all to the power of half. That is just if we solve for this one, Fermi momentum, cross multiplying that expression. So that is 2Ef is equal to mVf squared and multiplying throughout by m, then 2mEf is equal to m squared Vf squared. And mv nothing but what? Momentum. mVf nothing but p. So m squared Vf squared nothing but p squared. Then our pf squared say here. Pf squared is equal to 2mEf. So solve for pf. Then pf is equal to 2mEf all to the power of half. This is the expression for Fermi momentum which can be obtained by using the Fermi energy expression. Next, we are going to discuss application of quantum free electron theory to electrical conductivity. Application of quantum free electron theory to electrical conductivity. Okay, now we are going to deduce an expression for electrical conductivity. Okay. So that we are going to use some basic concepts. Those concepts were discussed in lower class, that is PUC class, okay, class pre-university classes. Starting with the drift velocity in a conductor carrying current. The general expression for the drift velocity of free electrons in metal is Vd is equal to minus E by m into tau, where small e is the charge of electron and capital E is the electric field strength in which the electron is moving, and m is the mass of the electron and tau is the collision time or relaxation time. The definition of all these were discussed in PUC and this relation also derived. While deriving the expression for current through the conductor, that is I is equal to NEA Vd, we are discussed this drift velocity concept also. So again, in metal, current density J is given by J is equal to I by A. That I is equal to NEA Vd, where A is the area of cross section of the current carrying conductor. So if we solve for current density, that is J equal to I by A, we have J equal to NE Vd. Now substitute the value of drift velocity here, then we get J is equal to minus NE squared tau E divided by M. Let's call this as equation 2. But from definition of this electrical conductivity sigma, we have sigma is equal to minus J by E. It is the ratio of the current density to the electric field. The current density gain per unit electric field strength is what we call electrical conductivity. That is represented by using the symbol sigma. Sigma is equal to minus J by E. Now substitute the value of J here and simplifying we have sigma is equal to NE squared tau by M. This is the expression for electrical conductivity in terms of relaxation time tau. That is sigma equal to NE squared tau by M. Important. There will be a problem on these relations. So let's call this as equation 3. If lambda is the mean free path and Vf is the speed of free electrons, that is Fermi velocity also, whose kinetic energy is equal to Fermi energy. Whose kinetic energy equal to Fermi energy, since only electrons near Fermi level contribute to the conductivity. Only electrons near Fermi level will contribute to the electrical conductivity. The electrons which are present deeper in the metal, those electrons may not gain any sort of energy and they may not take transition or to the electronic levels above the Fermi level. Those electrons what we call free electrons. So the deeper electrons always bind to the metal or atom inside the metal. Therefore, the average time tau between collisions between any two electrons, successive collisions between any two electrons is given by, that is tau is equal to lambda by Vf. In terms of mean free path, we are going to define the relaxation time or mean collision time or average time, okay, of collision. The tau is equal to lambda divided by Vf, where lambda is the mean free path, okay, the average distance between any two successive collisions between the free electrons. That is what we call mean free path. So tau is equal to lambda divided by Vf. Substitute the value of tau in the previous expression, that is equation 3 here. In the place of tau, we are going to replace lambda by Vf. We have an expression for electrical conductivity as sigma is equal to Ne squared lambda divided by mVf. Ne squared lambda divided by mVf. Let's call this as equation 4. This is another expression for electrical conductivity in terms of mean free path. Next, we know that the Fermi energy expression as Ef is equal to half mVf squared. Again, that is equal to 3 by 2 kT. The energy associated with each free electron is found to be 3 by 2 kT. Energy associated with 1 degree of freedom. Each degree of freedom is half kT according to laws of thermodynamics. Okay, here the thermal energy possessed by the electrons is nothing but the kinetic energy of the electrons, and that energy is given by 3 by 2 kT because each electron possesses 3 degrees of freedom. So 3 into half kT, that is 3 by 2 kT. Now by this expression we solve for mVf in equation 4. Therefore mVf is equal to, again 2 cancel, it's equal to 3m kT. mVf is equal to 3m kT to the power of half. Again multiplying throughout by m and simplifying for mVf, we have 3m kT to the power of half. Substitute this in equation 4, we get another expression for electrical conductivity sigma in terms of temperature and Boltzmann constant, that is sigma is equal to Ne squared lambda divided by 3m kT to the power of half. Let's call this as equation 5. This is another expression for electrical conductivity. We have one more expression also in terms of Fermi energy, but again we know that Ef is equal to half mVf squared. That is, okay, this implies if we solve for Vf, we have 2Ef by m to the power of f. Substitute this in equation 4 and simplifying, we have sigma is equal to Ne squared lambda divided by 2mEf to the power of half. This is another expression for electrical conductivity. Next concept, collision time tau as a function of Fermi energy. Okay, just now we discussed about the concept of collision time or relaxation time. Now the expressions also, once again we are going to use that expression. Collision time tau is equal to lambda divided by Vf, where lambda is the mean free path. And again we know the expression for Fermi velocity as Vf is equal to 2Ef divided by m to the power of half is the expression for Fermi velocity. Now again, if we solve for tau f, that is collision time at Fermi energy level or Fermi level, then tau f is equal to lambda by, substitute the value of Vf here, then 2Ef by m to the power of half. Here we found that the collision time tau is inversely proportional to square root of Fermi energy. For this instance, if lambda is constant and m is constant, then those are replaced by the given metal. Okay, proportionality, then tau f is inversely proportional to root of Fermi energy, square root of Fermi energy. This is what the relation between collision time and Fermi energy. Collision time is a function of Fermi energy. Also we know that electrical conductivity sigma is equal to Ne squared tau by m. Okay, from these relations it is observed that from electrical conductivity expression and this relation between collision time and Fermi energy or relaxation time and Fermi energy, it is observed that only in relaxation time some of the electrons at Fermi level or Fermi surface occurs in conductivity, while all electrons are taking a part in conduction mechanism. Only electrons at Fermi level occurs in electrical conductivity, will contribute to electrical conductivity, while all electrons are taking a part in conduction mechanism. Just they are participate to do the conduction mechanism, but they won't contribute to the electrical conductivity. The electrons which are present just close to the Fermi level, okay, where the time, okay, of this transition takes place from the electronic level just below the Fermi level to the electronic level just above the Fermi level. Okay, within that stipulated time tau, okay, whatever the electrons will present at the Fermi level will occurs in electrical conductivity expression or electrical conductivity, while all electrons are taking a part in conduction mechanism. Okay, with this I am going to, one more concept is there. It is failures of quantum free electron theory. This is the last concept I have to discuss in this session. Failures of quantum free electron theory. According to this model, electrical conductivity is proportional to free electron density. According to the quantum theory of free electrons or this model, electrical conductivity is proportional to free electron density. But monovalent metals have high conductivity than divalent or trivalent metals. This concept is not explained by the quantum theory of free electrons. Hence, it fails to explain the conductivity, high conductivity of monovalent metals compared to divalent or trivalent metals. Another limitation of the free electron theory is, according to this theory or model, Hall constant is negative. According to the quantum free electron theory, Hall constant is negative. But some metals have positive Hall constant, but that cannot be explained by this quantum free electron theory. This is one more limitation or failure of quantum free electron theory. And third limitation is, theory could not explain properties of semiconductors. This quantum free electron theory explains only the properties of metals, but it fails to explain the electronic properties or electrical properties of semiconductor. This is another major drawback of free electron theory. Okay, mainly these are the main failures or demerits or drawbacks of this one free electron theory. Again, we may ask 2 marks question on these concepts. With this, I am going to end the discussion of this session. Before that, I am going to brief once again the probable questions may appear in your examination. About this concept of Fermi temperature, there will be a 2 marks question. What is define Fermi temperature and explain in brief. So what is Fermi temperature? Explain. This type of question may expect in the examination. Next, Fermi velocity and Fermi vector. What is Fermi velocity? Write down the expression for Fermi velocity. That type of question may ask. Again, about this formula, we may expect some problems. Fermi vector, Fermi velocity and Fermi momentum concepts. Next, application of quantum free electron theory to electrical conductivity. Again, there will be a 2 marks question on this concept. They may ask for write down the expression for electrical conductivity in terms of relaxation time or in terms of mean free path or in terms of Fermi energy or in terms of temperature, and explain the terms in it. These type of questions may expect, and it is very important for problem part. They may ask some problems on these relations. And again, there will be a 2 marks question will be set on this topic, that is collision time as a function of Fermi energy. And the last concept is failures of quantum free electron theory. There's so many times this question, for 2 marks, there will be a question on this failures of quantum free electron theory in the examination. This is very important. With this, I am going to end this session. Thank you. Thank you, one and all.